we continue our discussion on piezoelectric transducers, and after showing importance of acoustic impedance matching between transducer and object that is investigated, we will now make a few comments about importance of electrical impedance matching between the acoustic transducer and instruments that are connected to it to process the signal. So the impedance is given with this relationship here in general, and we see that in reactance we have a frequency and capacitance. And now imagine that we are working with high frequency transducers, which are used to detect small objects. So the higher is the frequency, the smaller is the wavelength, and you know, is in any microscopy, with the smaller is the wavelength, the smaller object you can detect. So for high frequency transducers, this will be very large, and capacitance will also necessarily be very large. Why? Because capacitance is inversely proportional to the thickness, and the resonance frequency is also proportional to the thickness. So if you want high frequency, you must have low thickness, and that means high capacitance. So this whole term is very large. And when you look how impedance at resonance looks like, so this is impedance, this is frequency, and the impedance would look something like this. This is resonance frequency, close to this minimum point. And you want material that operates, your transducer that operates at these frequencies, to have impedance which is as close as possible to 50 ohms. Why is this so? Well, you want 50 ohms because that's input impedance of most instruments that are processing signal. And as we said before, you will get a maximum signal transmission, maximum power transmission if impedance of two instruments, of two objects are matching. So we need to make this as close as possible as 50 ohms. So it can be either too low or too large, and there is a lot of freedom in changing material, changing geometry, and so on. And one way to handle these things is with ceramic polymer composites. And to discuss ceramic polymer composites, I have to introduce several notions. First of all, we will use composites between piezoelectric ceramic and polymer which is not piezoelectric. So polymer is completely a passive material. Second, we can use this polymer for several purposes, and I will try to explain them. And third thing is these composites, polymer ceramic composites, in the field of piezoelectric composites have certain notation that you should be aware of. So we will say that composite has a 0-3 connectivity if we have that ceramic phase is embedded in form of small particles, let's say spherical particles, into polymer matrix. So this is polymer and this is ceramic. So you are already guessing. 0 is the connectivity of the ceramic phase. So it's point, 0 dimension, and the polymer is connected in all 3 dimensions. Then we have connectivity 1-3, in which ceramics are one-dimensional rods of a piezoelectric material embedded in a ceramic, which is again connected in all three phases. Then we have, for example, 2-2 composites. This would be polymer and ceramic plates. Ceramic is connected in 2 dimensions and the polymer is connected in 2 dimensions, but neither is connected in all 3 dimensions, and so on. This comes from work of Bob Newnham at Penn State and his team. They developed this notation, symmetry considerations, properties, and so on. And these piezoelectric ceramic polymer composites are now the most widely used transducers for medical imaging and underwater observation, listening. So what can you do? Well, one of the things that you can do with these elements is to make arrays. So you can have a single element transducer in which you have a monolith sample electroded on the top, and the whole sample oscillates. But sometimes what you would like to have is to have a array of transducers, and I am now drawing this from the top. Array of transducers where you can scan. You can fire one by one with the electric field. So you can scan, you can steer acoustic signal. You can use one of them to send signal, the other one to receive signal, and so on. And you can use one-dimensional or two-dimensional arrays and so on. But it is very inconvenient to produce a very large number of individual transducers. So one way to do this is to, instead of covering the whole surface of the sample, you can, well, sorry about that, you can electrode only certain parts, and then use this as individual elements. So this is all ceramic, okay? However, this is not good, because if you are doing something to this element, the next element will also feel it. Why? Because it's a solid material. This element, if it oscillates in this direction, will also oscillate in this direction, and the next element will read part of the signal that elements around it are feeling. So there will be a lot of crosstalk, a lot of coupling of the signals, and you will basically have a big noise. So to avoid that, you either use materials that have a very low transverse piezoelectric coefficient, such as lead titanate, but that's not very practical. Still, there would be a lot of leaking of a signal. One way to avoid that is to put these piezoelectric elements in a polymer matrix, and then the polymer matrix will absorb all transverse signals. And the third thing that you can do with these piezoelectric, with these transducers, the second thing is that making such a transducer and covering the whole surface. Okay, so you have these piezoelectric, individual piezoelectric element, but you electrode now the whole surface. Okay, so you use it as a single element. Now, this single element will have a high piezoelectricity of individual ceramics. However, it will have a low capacitance because polymer has a lower capacity. These are connected in a parallel, so you would have that capacitance capacitance of ceramics plus capacitance of a polymer. But since capacitance of the polymer, the electric permittivity of the polymer is much, much lower than of ceramics, even though you add these two numbers, you would still have a much lower than if everything was, than if everything was made of ceramic. And also polymer will in arrays will absorb this transverse signal. I'm not sure if I'm forgetting. Yes, by putting polymer and using it in as a single element transducer, you would be also reducing the density, and therefore you would be matching impedance of such a composite with either water or a human body much better than if you have monolith ceramic piece. And so here it is. So you are getting good impedance matching, both electrical and acoustic. You have that lateral vibrations are removed. Okay, lateral vibrations are removed. Reduced. Then you have that crosstalk between elements is reduced, and the transverse resonances that you would get between these two elements are also reduced. So there are great advantages of using these piezoelectric ceramic composites. You see that ceramic piece is completely available to the acoustic wave, both for emission and reception. So polymer doesn't interfere with the piezoelectric effect, and but you reduce capacitance, you reduce density, and you reduce the crosstalk. You can also use this as an arrays because each of these elements is independent in the composite helped thanks to the polymer. You even get that the coupling coefficient, the thickness coupling coefficient of such composite is bigger than even in a pure ceramic. And that has to do with the fact that each of these elements is somehow free, and the K33 coupling coefficient is bigger than KT. Thickness coupling coefficient KT for a plate is always smaller because there is a Poisson ratio which is which plays a big role in such two-dimensional structures. So as I said, these are widely used. Almost a majority of the acoustic transducers used for medical imaging and for sonars are today made with these transducers. They also show a less ringing, and I would like to explain what this is. So here is one acoustic probe, ultrasonic probe for abdomen, using to look in your stomach. And usually when you apply a pulse, you see that the signal will persist. So you apply a pulse, electrical pulse, but the acoustical signal would persist for some time. That is called ringing, and that's because of here you have I think 64 elements, and these elements would talk to each other due to transverse coupling and so on. However, when you make a composite, so this is just ceramic, and this is, so when array is made just of a ceramic, and this is when array is made of a composite. You see that signal duration is much shorter than if you have the whole array made of ceramic material. So this works very nicely. Here is an example of a 2-2 composite, and as I said, you can so this is a one-dimensional 2-2 composite, one-dimensional probe. It can be 32, 46, 128 elements. This is two-dimensional probe, or if you electrode the whole thing, then you would get a single element. Now, one has to see again these electric impedance matching requirements are different. In this case, if you are using it as a two-dimensional probe, these elements will have a very low permittivity, and it can be too low. Okay, because remember, capacitance, sorry, not permittivity, capacitance. Permittivity doesn't depend on dimensions. So capacitance is equal to this. So this is fixed, but for something that is very long and narrow, area is small, thickness is large, and this whole capacitance becomes very low. So you may have a too low impedance. Also if it doesn't operate at very high frequencies. Here, on the other hand, since, again, because of the capacitance, you need small permittivity. You cannot use a large permittivity because the capacitance would be very large. So you need to reduce capacitance a little bit. So there are different considerations, and this is how you choose your material for different applications. Another one is that in this case here, we need a high K33 coupling coefficient. So that's the coupling coefficient which works with this geometry. And here we need high thickness coupling coefficient. So small permittivity, high KT, and here we need large permittivity and high K33 coefficient. So one material cannot satisfy all the requirements. So you have to look which material to use. Okay. And that is why you have to understand what these different things are doing when you are choosing your material. Now, if this is done very carefully, you can get, there is a huge progress in ultrasonic transducers, what has been accomplished. You can get three-dimensional pictures, for example, of fetus. You can see details of organ, of blood vessels. You can use this for a diagnosis. Also, as we will discuss later, you can use piezoelectric effect also for treatment, but that will come later. You can use this also in tomographic form to look in a body at a different depth, and then slice with a software basically, and see three-dimensional picture inside. So this is a look at the brain, just like NMR is doing. So single crystals of relaxer ferroelectrics are very good here for some of these array elements. They have very large D33, very large K33, which reaches 0.9. So the energy that is transformed from input to the output energy can be 80%. You can also use them in a shear mode in which they are at some cuts very large D15 coefficients. Same transducers with the same geometry, just different size, are also used for underwater applications. And underwater, you use them for fish detection, so for fish harvesting, for object location. This is how you find a ship under the on the ocean floor. This is used for mining and oil industry. By scanning the bottom of the ocean, if there is deposits and so on, you can detect them because impedance will be changing, and also piezoelectrics are used as piezoelectric actuators to drill the ocean floor. And for vessel location, for location of submarines and so on, and these are called sonars. So the ships would have behind them sometimes a few miles long array of transducers which they use to detect the submarines. For submarine detection, so these are military hydrophone sonars. As I say, they are exactly same as those used for ultrasonic imaging in medicine. Nuclear submarines could have several dozens tons of PZT for sonars inside. So the huge amounts. This whole part is a big sonar in a submarine. And submarines are the sonars can be used in passive and active mode. Passive when submarine is just listening, and active when submarine is sending the signal and then receiving a reflection from it. Of course, when you send signal, then others can detect you too. So there are all kind of strategic considerations here, how to use these things and so on. Just to tell you how powerful these sonars are, if ship starts engine in New York, the acoustic signal of that ship can be picked up in England by a sonar. And not only that you can pick up that signal, but that you can also tell which ship has started engine. And this is possible because every ship has some signature, you know, like fingerprints of our hands. Some fish use also piezoelectric effect to communicate, or similar effect to communicate. For example, whales can talk to each other on distances of hundreds of kilometers. So these hydrophones for naval application in submarines can be big as a house. As I said, several tens of tons of a PZT. And one thing that can happen with these sonars is that the sound that they are producing can be huge. The sound intensity that they are producing can be 120 or even more decibels. And if 120 decibels is very large sound in air, you can imagine how much powerful it is underwater. So it is a thought that many of these strandings of, you know, when they find dolphins or whales on stranded somewhere on a beach, people suspect that many times it was done either from underwater drilling for oil and mining reasons, which also creates huge noise, or done by these sonars from exercises or either ships or submarines. Doesn't have to be military necessarily, because other ships also have these sonars. what they basically do is the pressure underwater is so big that it simply destroys the brains, internal organs, usually a brain of these mammals. You can use ultrasound to detect fingerprints, and this is much better than optical. Because when you put your finger on an optical machine, sometimes you close these pores and it's not always very effective. With the ultrasound, it will very accurately detect all valleys and ridges on your finger. And I think Samsung is now using ALN, aluminum nitride resonators, for fingerprint detection when you want to enter your phone, computer, and so on. You can use it to test the surface. I'm sorry that I don't know the references from which I took this. Here is the scanning with the ultrasound of surface of a coin. And you really can do it very, very precisely, and you would be able to reconstruct the surface later on. So the higher signal is where you have a higher height from some base level. Now the new trends in imaging is to go to very high frequency applications. We are talking about 100 megahertz range, where you can see sub-millimeter objects, for example, for a skin cancer, for ophthalmology, and so on. And there are challenges in producing small elements, and there is always deterioration of properties with size reduction, because you have to do a lot of machining, and that can induce defects and so on. People manage to do this, but it's difficult, expensive, and few companies are able to do that. So basically, you would have to work with for 100 megahertz, you would have to work with the thicknesses of about 20 microns. This can be done. There is no problem. There is no difficulties that cannot be surmounted, but it's not trivial. You will also have in such small elements non-linearities, because fields that you are applying on a sample are now very large, and then there will be non-linearities that you also have to deal with. So here is a Jomed Doppler device, the catheter, which at its end, it's just 300 micrometers in diameter, and I think it has 64 piezoelectric elements inside. So imagine putting 64 elements on 300 microns. So they are distributed around the perimeter of this 300 diameter, and then you can look in all directions when this enters into your blood vessels, and it can go all the way to heart to see what's happening there. Of course, one way to get these small elements is to use very thin piezoelectric films. And here is one. This is silicon. This is platinum electrode. This is platinum electrode, and between them there is a PZT element, which is just few microns thick. The problem with this is that when you make thin films, you have to deposit them on some substrate. And when you drive a substrate, when you dry a film, you will also drive the substrate. So part of this energy will be given into the formation of the substrate. So the coupling coefficient of thin films is always much smaller than the coupling coefficient of the bulk material, or material that stands alone. Of course, you can make PZT standing alone if you cut down, if you micro machine the silicon, but that has other difficulties. So you can make suspended membranes and so on. So there are ways in which this can be done, but in general, thin films will give you low coupling. So this finishes our part on transducers, and we will finish the course with a number of other devices which I think are interesting.